Yeah. Okay, great. Thank you, Stella. So hi everyone. Thank you for coming to our 5th training series in our series. Today's training session will cover IRT equating and provide a demonstration of a software program, IRT EQ, that can be used for IRT scaling and equating. I'm Jaime Malatesta, and I am a co-chair of the SLE SIGME, along with Stella Kim, who is the other co-chair. I will be teaching the first segment of today's session, where I go over IRT equating for unidimensional tests. I'm currently a lead psychometrician at the Graduate Management Admissions Council, where I work primarily on the NMAT exam, which is like the international version of the GMAT exam. Following my training session, Dr. Kyung Han, or Chris Han, will provide a demonstration of his free software program, IRT EQ, which can be downloaded freely from handtest.net. And Dr. Han is the Senior Director and Head of Test Development and Psychometrics at the Graduate Management Admissions Council, and he's also my boss. So thank you so much, Chris, for taking the time today from your busy schedule to be here with us. So during the session, I ask that you use the chat feature to ask questions, and I'll circle back to them at the end of the session. And we will also be taking a break in between my session and the following demonstration by Dr. Han. So during that break, I'll take the time to go through any of the questions that you've asked, and I will address them once Chris has finished his demonstration of his equating software. So now I'm going to go ahead and share my screen. Okay. Let's see, here we go. Okay, can you see that okay, Stella? Good, okay, great. I'll get this out of the way 1 second here. Okay. Okay, so the topic of our session today is IRT equating methods. And I will be primarily presenting on an example that uses the 3-parameter logistic model, which is a unidimensional model. So next week, Stella, I believe it's next week, or coming up next, Stella will be talking about multidimensional IRT equating methods, so I won't be covering that today. Also, this session, assumes that you have a prerequisite knowledge of basic IRT concepts and IRT principles, so I'm not going to go over much of that either. And also last week we had a training session that covered scale linking, IRT scale linking. So predominantly the majority or all of this talk today will be with the understanding that IRT scaling has already been done, so that the form X, or the new form, item parameter estimates and person parameter estimates have already been placed on a scale of the old form Y, which is, I'll go over our notation here in a minute as well. So if for those of you who are not familiar with how to do IRT scale transformation, I recommend that you go back and watch the previous training session from last week, where that is covered as well. Okay, so for the majority of our session today, I will be going over equating when we use the theta scale or the theta metric, and then also equating in situations where we use a number correct score scale. And really this is the true equating, is when we use number correct score scales for reporting purposes. We typically think of IRT true score, IRT observed score equating methods for handling those cases. I'll also go over briefly how to equate to a calibrated item pool, and how pre-equating is typically done. And then following this, we'll take a break, and we'll have Dr. Han demonstrate how to use the IRT EQ software for doing these equating procedures. Okay, so the notation I'm going to use today largely follows from the Colin and Brennan 2014 textbook. That's what I was taught with, and so that's what I'm used to using, and so that's what I'll be using today during our presentation. So form X is the new form Form Y is the old form. Group 1 are examinees who took Form X. Group 2 contain examinees who took Form Y. The theta is just the IRT theta, our examinee ability estimate. TCC refers to the test characteristic curve, and CINEG is the common item non-equivalent group design. So you'll see these notations throughout the presentation. So first, as I mentioned, I'll be focusing on the 3PL parameter logistic model. We're here just to go over the brief probability. You see we have the probability that candidate or examinee I correctly answers item J is given in this equation, where A refers to the item discrimination, B refers to the item difficulty, and C refers to the item pseudo-guessing level for item J. And D is a scaling constant equal to 1.7 roughly to make the probabilities an equal or an approximate, make the probabilities an approximate modeling of the normal O-drive model. So this is it's not exactly the normal O-drive probabilities, but the probabilities are very close to the normal O-drive probabilities, which is what IRT was originally founded on. So that's why we use that. And then the EXP is just the natural exponent. Okay. So here, we have our IRT assumptions. So, with the regular equating that you have done in the past, or that you were trained on earlier, we had our own assumptions for those traditional equating methods, right? But now we have, since we're using IRT, we have an additional layer of assumptions that we need to pay attention to when we use the IRT equating methods. And so these assumptions really are just the IRT, item level assumptions that you are all probably familiar with. The unidimensionality assumption that the item measures just a single construct, also made at the test level. The test measures a single construct. Local independence, that the probability that of an examinee and correctly answering an item correctly or incorrectly depends solely on their ability and nothing else. So, their probability of correctly answering one item should not be related to the probability of a candidate correctly or incorrectly answering another item. So these probabilities are independent. And third, the form of the item characteristic curve. So we have to check that our model fits the data appropriately. And so there's, techniques to do that. So these three assumptions for unidimensional IRT models are required and should be checked and verified with, using all reasonable measures available prior to using an IRT equating method. So as stressed in the Coleman and Brennan book, we should design equating procedures so that the effects of violations are minimized. So we definitely strive for that. And IRT assumptions are made at the item level, and so they're stronger than some of the classical equating assumptions. But if these assumptions are met, IRT allows for greater flexibility compared to classical equating approaches, which we'll see here in later on in our training, how that plays out. So if we have a situation where we're reporting scores on the theta scale, or we have a reporting scale that is a linear transformation of theta, meaning that we're not using number correct scoring, we're using a theta scoring of some sort for our program, for our testing program, then actual equating is not necessary and scale linking is sufficient. So as long as, so here we refer this situation as scaling or IRT scale linking. We use methods, if we have the common item non-equivalent group design to start out with, then there's methods that were discussed last week, such as the mean, the mean sigma, stocking Lord, or the Habar methods that can be used to place the item and person parameters on form X onto the scale of form Y. And so, or under the common item non-equivalent group design, you also have you can also use simultaneous parameter estimation, or also known as concurrent calibration, where you lump data from form X and form Y together, and you have the common items overlapping between the two forms, and you do one run of, say, Bilog or FlexMert, and so in that sense, items and person estimates are placed on the same scale. And so that's the scaling that, sets the score scales to be comparable across the two forms when you're using the theta scale for reporting, or linear transformation of the theta scale. So, theta scale is not very informative. I mean, it is informative, but for a layperson or someone who doesn't understand what IRT is, interpreting scores that are negative and non-integers can be very confusing, right? So typically what's done is you create a theta to scale score conversion table, and it can be a linear conversion table typically, that results in an integer scale score, a positive, with positive values that range from 0 to, whatever you decide to set the maximum scale score to be. And so in those situations, you wouldn't need to actually have a true equating per se procedure. With the random groups design, similarly, this is like a spiraling design, right? So you would randomly spiral the old form and the new form to a particular population of candidates or examinees. And using the same theta mean and standard deviation for IRT calibration of those two forms, you would those two forms then would be on the same theta scale or theta metric. And so if you were to use theta as your reporting scale, then this would be your final step. Once you've converted your thetas to scale scores for reporting purposes, you would not need an additional layer of equating. Okay. But using the theta scale has its own drawbacks and own complications. So typically for the 3PL model, the entire 0-1 response scale is used to estimate theta, and not just a simple number correct score. So if you're using something like the Roche model, where a number correct score is sufficient statistic, then this issue is not really relevant. But a lot of times the 3PL model is used in practice, and so in that situation, examinees with the same number correct score can have different theta estimates, and so that creates an interpretational problem when you're reporting scores to examinees. Someone will say, I have the same number correct score, but I have the same number of answers of items correctly as so-and-so, but we have different reported scores, and so trying to explain that can be tedious. Also, the ability estimates based on the 3PL model, they have really large amounts of standard of measurement error at the tails. So very low ability candidates and very high ability candidates, they're going to have much more measurement error compared to those people who are around the average ability. And there's ways to get around that, but that's a known feature of the 3PL model. So for that reason, sometimes people prefer to use number correct scoring instead of relying on theta scoring or the theta scale for reporting purposes. And when you choose to do that, then you are required to do an additional step of equating. And in that situation, we have IRT true score equating and IRT observed score equating, which I'll go over next. Okay, so for IRT true score equating, you have true scores on form X that are associated with a particular theta, and they are considered equivalent to a true score on form Y. So that's the overall premise. Now this is the IRT definition of true score, which I will get into in a minute. So This requires, as I mentioned earlier, that these item parameter estimates and person parameter estimates for these two forms have previously been put on the same theta scale through a IRT scale transformation procedure, such as the Habara method or Stocking-Lord method. So true scores on form X and Y for the 3PL model are defined by the test characteristic curve, or TCC. And here is the general formula for true score on form X given a particular theta for examinee I. It is basically the sum of their response probabilities for all the items on form X. So that here the summation is J JX, so it's taken over the items on form X. And similarly, we have a true score on form Y, which is essentially the sum of the IRT probabilities or model-based probabilities for a person with a particular theta and their probability of responding correctly to each of the items on form Y. So for a given theta I, we assume that the true scores on form X and form Y, that they're considered equal. They're considered equivalent here. To show you an example here. So here's the basic procedure using a graphical demonstration. So true score equating for number correct scores on form X and Y. So this example is for a 36 item test scored using the 3PL model. And this example is actually given in the Pi equating software on the CASMA website. This is the data for that example can actually be downloaded for free, and you can try this out yourself if you go to the CASMA website and look up the Pi equating software. And I think it's also referenced in the Coleman and Brennan 2014 equating book as well. So in this case, we start out with step one. We specify a form X true score. So in this case, we'll start out with a true score, say 28. Okay, so this test has 36 items. Number correct scores range from 0 to 36. So for example, we're interested in a candidate who has a true score or who has answered 28 items correctly. So here we go to the test characteristic curve for form X, which is the blue line, the blue S curve, and you go down here and you look for the theta. You find the theta that corresponds to a true score of 28, and we find that theta is approximately 1.6. And then, so that's step two. Step three is you take that theta and you find the corresponding true score on form Y for a theta of 1.6. And if you go back up to the test characteristic curve for form Y, which is in red, you get to this point and you go over to the true score and you'll see here it's about 30. So true score on form Y is about 30 in this case. So step one is pretty straightforward. It's just finding the test characteristic, summing over the probabilities for a given candidate. Step two requires a numerical procedure. Actually, it's not that straightforward, but typically the Newton-Raphson method is used to find it's a numerical method that's actually used to find this theta estimate. And I thought for the purpose of this presentation, it was probably a little bit too involved to get into that numerical method, but it's outlined in detail in the Coleman and Brennan book in chapter 6. So if you'd like to know the numerical details of solving the nonlinear roots to find this theta estimate, I highly recommend you go there. And there's a worked example where they walk you through how this computation is actually done. But this is the general idea and the steps involved with IRT true score equating for a dichotomous test. Let's see here. So true score equating, it can be done without specifying the examinee ability distribution. This is a big reason why IRT true score equating is used in pre-equating contexts, because you don't need to specify the ability distribution. All you need here are for inputs are the item parameter estimates and the range of number correct scores on Form X. And the computations are relatively straightforward compared to IRT observed score equating, which we'll get into in a minute here. And like I said, this is why IRT true score equating, I think, is used more commonly in practice, because it allows for this pre-equating context where you can come up with the raw to scale score conversion table prior to even administering your exam to candidates, as long as you have the IRT item parameter estimates available, and you obviously know the maximum number of items or number correct score range for your tests. You can go ahead and create these raw to scale score conversion tables before even giving out your exam to candidates. But there's some caveats with IRT true score equating. So this equating relationship, it's established for true scores, actually, but in reality, we're applying the true score relationship to observed scores. And so there's no good theoretical justification for doing this, except that we've seen in the literature that the true score conversions are similar to observed score conversions, and so the results are meaningfully similar. So in practice, we apply the true score equating relationship to observed scores, because true scores are, really unknown in practice, right? We don't ever truly know what true scores are in practice. When using the 3PL model, the IRT true scores, they're undefined below the sum of the C parameters and for perfect scores. So for candidates who score, say, for this example, for the 36 item test, the sum of the C parameters was around 7. So if you sum the C parameters across all 36 items, it comes to about 7. So if candidates were to score, a 7 or below on this new form, then the true score equating relationship is really undefined for that range of candidates. And so we use like an ad hoc approach, like a linear interpolation or a truncation for those candidates where we cannot estimate their true score. And so there's some additional, error, obviously there's additional error incorporated into those equated scores for candidates who are very low ability. But you can avoid this, problem if you choose a different IRT model, like the 2PL model or a Roche model, 1PL model, something like that. Or the IRT observed score equating approach, which I will talk about next. Okay, so again, for IRT observed score equating, the prerequisite that we have is that examinability and item estimates have been placed on the same scale using some type of IRT scale transformation procedure. There's two general steps. So the first step, using the item and ability estimates for Form X and Form Y, you estimate the number correct score distributions on each form separately. Okay, so you're essentially getting a smooth Form X distribution and a smooth Form Y distribution for number correct scores. So this relies heavily on the local independence assumption that allows us to multiply probabilities across items. We assume errors are uncorrelated. And so that's why that particular assumption is very critical, especially when you're using IRT. It's always critical when we're using IRT, but you'll see here in a few minutes, especially how this assumption is relied on heavily when we're computing these marginal observed score distributions. So once we have these observed score distributions estimated, which I'll show you how to do in a minute, once we have these two observed score distributions for Form X and Form Y, what we do is essentially use a classical equipercentile equating method to equate the Form X distribution onto the Form Y distribution. So to make those two distributions equivalent. Okay, so here's an example of how we estimate observed score distributions for Form X. Okay, so for this example, we have ability, someone with ability denoted theta I They have taken a 3-item exam just for ease of demonstration, Form X. The probability that an examinees with this ability answers either no items correctly, 1 item correctly, 2 or 3 items correctly is what we're going to go over right now. So typically f of x equal to 0 implies that they answered 0 items correctly. And to get this probability, f of x equal to 0, it's essentially you multiply 1 minus the probability of answering the first item times 1 minus the probability of answering the second item correctly times 1 minus the probability of answering the third item correctly. So you multiply these 3 terms and then you get the probability that a candidate with ability I scores a 0 on this exam. If you want to look at the probability, compute the probability of this candidate getting an observed score of 1, x equal to 1, you have this longer equation, right? So we have the probability of them correctly answering item 1 times the probability that they incorrectly answered item 2 times the probability that they incorrectly answered item 3. Then you plus, or they could possibly, so there's 3 different ways that they could score at 1. So in this first group of terms, we're assuming, or the first way they could score x equal to 1 is by getting item 1 correct, but getting items 2 and 3 incorrect. The second way they could get a score of 1 is by getting item 2 correct, but getting item 1 and item 3 incorrect. So this is the second term here multiplied. The third way that they could get a score of 1 is by getting the third item correct, PI3, and getting the first and second item incorrect. So there's 3 different ways of getting a score of 1, basically, and we add those 3 probabilities up to get their overall probability of this candidate getting a score of 1 on this 3-item test. Similarly, we do the same thing for the probability of getting a score of 2, x equal to 2, on this 3-item test. So here, again, there are 3 different ways they can get a score of 2. They can get the first 2 items correct, so PI1 times PI2 times the probability of getting the third item incorrect, 1 minus PI3, or they could alternatively get the first item incorrect, so that's 1 minus PI3 times the probability of them getting the second and third item correct. Or lastly, they could get the first and the third item correct, but answer the second item incorrectly. So that's the last term there. You sum those terms together and you get the overall probability that a candidate with theta I answers 2 items correctly out of this 3-item test. Lastly, we have the probability of a candidate getting a score of 3 on this 3-item test, and it's simply the product of the individual probabilities for each item. So the probability of them answering item 1 correctly times the probability of them answering item 2 correctly times the probability of them answering item 3 correctly. You multiply those 3 probabilities together and you have f of x equal to 3. Okay, so as you can see, as your test gets longer, this formula gets more tedious and more time-consuming and harder to track. So as a result, Lorwin-Gursky in 1984, they came up with a recursion formula that can be used to generalize this general idea to exams that are much longer. And so the Lorwin-Gursky recursion formula defines f of r x given theta as a number correct score distribution for the first r items for examinees with ability I, theta I. So here we define f of 1, so r equals to 1, so they've seen 1 item. The probability of getting that item incorrect is simply 1 minus the probability of getting that item correct. So that's the probability of getting a score of 0 on the first item, and f of 1, x equal to 1 is simply the probability of that first item getting that item correct, as we saw on the previous slide. But for r greater than 1, this is where the recursion formula comes in, and it's basically this second line here, where when x is greater than 0 but less than the maximum number of items in the exam, we have this formula here, which is a little tedious to go over, but I'm going to go over a worked example on the next slide. So this is essentially the Lower-Wingersky formula, and this is as complex as it gets. So even when we have a 36 item test, we don't have this huge string of 36 potential ways of scoring a 36 on a 36 item test. So let me go over this with you. Okay, so here's a worked example. Examinee will say their theta estimate is 0.3. This is an example with a 3-item test. The probability of this candidate getting the first item correct is 0.975. The probability that this candidate gets the second item correct is 0.669. The probability that they get this third item correct is 0.303. So those probabilities are over here on the right-hand column. Okay, so when r is equal to 1, when they've been given just one item on this test, they can either have an x equal to 0 or an x equal to 1. So to compute x equal to 0, that they got a score of 0 on the first item, it's just simply 1 minus the probability of them getting that item correct. So 1 minus 0.975, you have this resulting probability of getting this item incorrect is 0.025. So we have these two probabilities here in the red and the purple. Okay, so now we give them a second item. So now this candidate has seen 2 items. Well, they can either have a score of 0, 1, or 2 after they've seen 2 items. And so the probability of them getting a score of 0 after receiving 2 items is this first line. It's the probability of them getting a 0 after receiving 1 item, which is the 0.025, multiplied by the probability that they incorrectly answered the second item, which is 1 minus 0.669. You multiply these terms together, you get 0.008. So that's the probability that they incorrectly answered both items. Okay. Now we have the probability. So what's the probability that they got one of these items correct? So they've seen 2 items, r equals to 2, x equals 1. Well, there's 2 terms involved here. The first term is assuming that they got a 0 on the first item. So they got a 0 on the first item, 0.025, times the probability that they got the second item correct, 0.669. So that's PI2, 0.669. Plus, or the probability, so then this is the other scenario that could have played out. They could have gotten the first item correct, which is the probability of getting the first item correct is 0.975, multiplied by the probability of getting the second item incorrect, which is 1 minus 0.669. So you sum these terms together and you get 0.34. So the overall probability that this candidate with theta equal to 0.3 got a score of 1 after seeing 2 items is simply this formula, what I just went through here, 0.34. Lastly, they could have gotten both items correct. So what you do then is you say, well, the probability of them getting both items correct is simply the probability, the 2 probabilities multiplied together. 0.669 is a probability that the candidate answered item 2 correctly, and 0.975 is the probability that this candidate answered item 1 correctly. So you multiply those 2 probabilities together, you get 0.651. So that's the probability for that. So, I mean, so this is a range, right? And that just continues on. So for when you get down to 3 items, that same logic, continues. And I highlighted the color-coded these probabilities to try and make it easier to track where they are coming from. So let's do this first line here. So we get to a 3-item test, R equals 3, X equals 0. We assume if the X equals 0 when they've seen 3 items, then we know that X equals, that when R was 2 and X was 0, the probability was 0.008. So the probability of answering the first 2 items correctly or incorrectly is 0.008 times the probability that they answered the 3rd item incorrectly. So here you have this 0.006. And so this logic just continues as you move forward. So you're constantly reusing the probabilities that you found in the previous step, or in R-1, basically, and using those probabilities as you go on further down the line, as this candidate is receiving more items, or you're adding more items to the exam. You just continue this logic. Oops, sorry. And so here, this distribution here, we have a candidate with theta equal to 0.3. They have a probability of getting a 0, a probability of getting a 1, a 2, and a 3. So what we're really computing here is a distribution of measurement error, right? We don't have an exact point estimate yet for this candidate. We have this distribution, this probability distribution for this candidate, or for these candidates with this given theta level. And so now we need to actually come up with a point estimate, right? So I'll show you next, this is just for a given theta level equal to 0.3. So what you would do is you would take, all of your theta estimates and repeat this Lohr-Wingersky formula to get a distribution of number correct scores for each theta estimate that you have for form X. Okay, so that's where the marginal distribution comes into place. So what we just went over was a conditional distribution, which is conditional on a given theta level. But what you need to do IRT observed score equating is the marginal distributions of number correct scores. So to get that, what you what you need to do, you need to get f of x, which is the marginal distribution for form X. And here what you do is you integrate over theta, the number correct score distribution, f of x given theta, that was found using the Lohr-Wingersky formula, and which is essentially weighted by the distribution of thetas in your population, or what you define as your population, and the densities in your population. But in practice, this integration is typically replaced by a summation. And usually you can use a posterior theta distribution that you would get from, like, say, bilog, or you can use like a standard normal quadrature distribution with a set number, 40 or so theta values with associated weights or densities. And so we have this f of x at the bottom, which is simply a summation over all your thetas. You sum your conditional number correct score distributions and weight those by your ability distribution. Okay. So here's an example, okay, of how we would do this in practice. Computing the marginal score distribution via summation. So you're essentially getting a weighted average of the f of x given theta across the quadrature distribution in this example. So here, from our previous slide, we were working with, excuse me, hold on. Okay. And a candidate with a theta of equal to 0.3 here, you'll see in the far left-hand column. Well, in that distribution, in that group of candidates who took Form X, the weight associated with a candidate who has this theta is 0.4. So, and the last step of the Lohr-Wienerski formula that I showed, we have the 3 items, the probability that this candidate with ability equal to 0.3 scored a 0 was 0.006. And the probability that candidate with the theta equal to 0.3 scored an x of 1, or observed score of 1, was 0.24. The probability that candidate received a score of 2 was 0.557. And the probability that the candidate received a score of 3, or answered 3 items correctly, was 0.197. So what you essentially do, you would have all of your thetas. So for this example, say we specify the theta distribution to go from -3 to +3. You would have the weights associated with each theta estimate, and those weights would sum to 1. And what you would do is you would multiply the weight. So in this case, the only value I have here, the weight is 0.4 for this candidate. You would multiply their probability of getting a score of 0 times their weight, and you would do that for every candidate, or for every theta estimate. So for every unique theta estimate that you have, you would have a row, basically, and you would multiply their probability of getting a score of x of 0 times their associated weight, and then you would sum these weighted probabilities to get the marginal probability for x equal to 0. And you would do the same for x equal to 1, to 2, to 3. So you would just be basically summing over these columns to get the marginal distribution, which would be here in the final row at the bottom. And you would do the same thing for form Y. So when you compute these marginal number correct score distributions, you have to decide on the theta, or what theta distribution do you use when you're computing f of x. And so I'm sure in the previous training sessions, this concept of a synthetic group, or how you define your population, has been brought up. But typically, when we define the synthetic group of W1, so this is the notation followed from Cullen and Brennan. So following that notation, when W1 equals 1, we say the synthetic group is made up of the candidates who took form X, the new form. And so when this is the case, the equated the groups that are to be equated are the distribution 1 is the form X number correct scores for group 1, or for those who actually took form X, and the form Y number correct scores for group 1. So those candidates didn't actually take, those examinees didn't actually take form Y, but we're using the transformed ability distributions that are placed on the form Y scale. And so here we're able to, so that's crucial. So you have to make sure that your ability estimates have already been transformed to the form Y scale prior to this step. Otherwise, your results will be completely inaccurate. So when the synthetic group is defined by those people who took form X, and W1 equals to 1, differences in form difficulty can be compared. So here, for this 36 item exam, this is an example of results using IRT observed score equating. We have the red line here is the identity equating line, meaning there's been no equating. No equating done. We assume a score on form X is equivalent to a score on form Y. And this reference line is really just used to gauge, like form differences. You can tell. So by referencing the equating relationship for the observed score equivalents and comparing those to the identity equivalents, you can see you know, is form Y easier or is form X easier, and so forth. So you can see here the blue line, which is the actual observed score equivalents using IRT observed score equating. They're slightly above the identity line for candidates or for examinees who scored, you know, roughly around, you know, 17 or 16 or higher. So in that case, form Y appears to be easier than form X because these candidates are I call them candidates now, candidates who they would have received, you know, for example, on form X, they would have received, for example, a score of 25 down here. Well, we see now that they're probably would have received a score of 27 on form Y. And so that allows us, we can look at the moments, the, you know, mean, standard deviation from these equating results, and we can see that in this case, you would, if we had them here, you'd be able to see that the form Y equated scores are generally higher than or larger than form X scores. If we were to take the same data, 36 item test, and compare IRT true score and IRT observed score equating results, this is something that would, for using the 3PL model, this is something that would typically be seen. So these, the dotted line is for true score equating. So this is the form Y equivalent minus the form X score. So this is basically the equated score on form Y minus their observed score on form X. And so this is a difference plot. And so you can see here that, you know, it's about on average for at the higher end of the ability scale, on average, you know, form Y is easier by about, I don't know, 1.5 points or something like that. But the trend between true score and observed score equating is pretty typical in that they're similar. The results are typically similar across IRT true score and IRT observed score equating, except for at the tails. So here in this example, we use a 3PL model, and the sum of the C parameters was about 7. And so for true score equating, the true scores are undefined in that range. And so we used an ad hoc approach, like a linear interpolation approach for this dotted line. You see it's very linear, this trend going from about x of 7 to x of 0. It's a very linear trend, whereas, and that's due to the result that we had undefined true scores in that range, and we use an ad hoc approach to estimate those equating relationships for those true scores. Whereas for IRT observed score, you'll see the equating relationship is a little smoother and doesn't depart like that. That's because we didn't have that same need for an ad hoc approach using the IRT observed score equating method. So in practice, this is, and again, so this similar, they're pretty similar overall, except for at the very low end and also for perfect scores. There are some differences, again, because true scores are undefined for that perfect score and using the 3PL model. Okay. Okay, so we can also use IRT equating methods to in a pre-equating situation and to build IRT calibrated item pools. And so typically, a lot of large-scale testing programs rely on these calibrated item pools. They're good because they can be continuously expanded each time a test has like a new form. They're typically pre-testing items, and these items then are continuously being added to these pools and expanding these item pools, and they're being scaled to be on the same scale, same metric as a pool that, or as a form that started the, well, you can select any form, but I'm going to go over that. So calibrated item pools allow for IRT pre-equating, which is why they're also beneficial. which also allow for immediate score reporting. So many testing programs have a desire or the need to do immediate score reporting. And so an IRT pre-equating using true score equating is what they commonly rely on. So here we have an IRT calibrated item pool on the left, where the scale is set by form Y, meaning that form Y was the old form, the first form that was given for this testing program, and it kind of sets the scale. So everything is placed on the scale of form Y for this item pool, for this item pool example. From this item pool, we can build a new form, form X, and that contains two different types of items usually. Items from the item pool that have already been calibrated and scaled to the form Y, so they've already had their item estimates estimated. They've already been administered to a group of examinees, and they've been calibrated and scaled to form Y. But in addition to those items, you typically have new items that are typically called pretest items or field test items, meaning they've never been given, typically have never been given to any candidates. They're brand new, and you need to collect data for those items. So typically they're spread out, and there's different ways to spread them off across your form X or your new form, but those typically are not scored. They're not scored, and so what happens is you collect data, you administer these new items along with your old items from the pool, and you're able to then estimate their item parameter estimates for the new items, and using the information from the older items, you're able to scale the new items onto the scale of your calibrated item pool. And so each time you administer a new form to a set of examinees, you're able to collect data on these additional new items or pretest items and calibrate them and scale them and add them to your pool so that they can be used next time for scoring purposes. I'll show you another example here. So more detail on how to build an IRT item pool. So step one, you would develop and administer form Y or your old form. So form construction, the administration, item calibration, scoring procedures, they're all set, they're done. So at this point, form Y is essentially your item pool, even though it's not really a pool, it's just your form Y, but that's what is in your item pool at this point. Then you develop and you administer a new form, we'll call it X1. And this form contains items from form Y and then new pretest items. So you estimate your item parameters and examinability. Using the items common to form Y and X1, so those common items, you obtain your scale transformation coefficients, and you place all of your items on X1 onto the form Y scale. So now, at this point, your pool now contains items from form Y and X1, and all of your items have been placed on the scale of form Y now. So your pool has gotten a little bit bigger, depending on how many pretest items you have. Step 3, you develop and you administer a new form X2. And this can go on to X, however many forms you're going to have. So the same thing follows for that form. It contains items from the pool and new items or pretest items. You estimate the item and ability parameters for form X2 and place those on the scale of form Y using some scale transformation procedure like the mean sigma, Habara, stalking lord, using the common item design. And so now those items, now your pool contains the form Y items and the new forms from X1 and the new items from X2. And so your pool is continuously evolving and getting bigger. So, but there are some considerations with using the IRT calibrated pools. So first, the item positioning of common items. So as you have more and more exams that are contributing to your item pool, and then you're building these new forms, you're going to want to maintain, as close as possible, you're going to want to maintain item positioning. So it's harder to do with computerized adaptive tests because they are adaptive match candidates' ability levels. And so a lot of times, I think in CAT context, these positioning rules, these context effects might be more pronounced and might, potentially lead to larger sources of error than if you had a typical linear form. But these context effects can be somewhat minimized if you randomize. If you embed your pretest items as opposed to making them a separate standalone section in the exam. So it's typically better to embed these pretest items along your intermixed in with your scored items. So they're not just all lumped at the end or all lumped at the beginning or in the middle. You want to have them dispersed kind of throughout the actual exam. So that's one way you can minimize these context effects. Also, when you're starting out with building an item pool, and if you want to use this approach to kind of like use the equating back to an IRT item pool is what I would say. If you want to use this approach, you need to think about multidimensionality and how it can be imposed. How it can pose greater risks in this context. So you have now these items are coming from multiple different forms, potentially, dozens, hundreds of forms, and now they're being put together on like a new form. And so sources of multidimensionality might creep in a little bit more than a traditional linear testing situation. So also when you're building this exam or this type of calibrated pool, you can safeguard by, say, using the common item design. You can carry out classical equating methods simultaneously until you're confident that your IRT calibrated pool design is working properly. So what you could do is, say you have a new form X4, and it has a set of common items. You can have two sets of common items. So you can have one set of common items overlap with a single form, say form Y or form X1 or form Y. And you could use that common item set to do a traditional equating, like an equipercentile method or something traditional. You can have a second set of common items that would be, that could come from the pool. That could come from, so form Y, form X1, X2, X3. So that second set of common items would actually mimic what you would actually do with a real calibrated item pool situation. And then you could carry out your scale linking and equating using that common item set as well, and compare your results. And so you would want to carry out kind of like the safeguard check. Having these two sets of common items simultaneously allows you to verify over some time that your procedures, your IRT procedures, are actually working as expected. And so that's a recommendation that is used quite often when you're first starting out building this calibrated item pool. So another issue with calibrated item pools and pre-equating is that any issues found after the exam is delivered. So if you're using, so this exam is delivered, and say you find an item that has a missed key or possible two keys or some type of content issue, this item is going to have to be deactivated, or it shouldn't be scored, okay? But you don't find this until after you've gone through your administration, your scores have been reported to candidates because you use some type of item or IRT pre-equating with true score equating. And so, candidates have already received their scores, but in real time, right after they take their exam, they close out the exam, they get their score. A lot of times it's right there in the testing platform, in the testing center, they get their score, but then you're doing your item analysis, checking, as we typically do. We check for bad items all along the administration cycle as the test is being delivered. And so sometimes these problems arise where you have these miskeys, and you have to actually correct your scoring and then report your scores to candidates or examinees. And so that's a risk with pre-equating, that you'll have to communicate this to your examinees, possibly if you find an item that was bad but that was used for scoring that actually should not have been. So that's a risk as well. So overall, some concluding comments. IRT equating methods have the following benefits. So, I mean, they're flexible. They're flexible in the sense, especially with the IRT calibrated pool, where you're not stuck, you're not limited in a common item situation. With a common item design, you're not limited to equating back to just a single form. You can equate to a collection of forms, basically, using an IRT calibrated item pool. Also using the IRT equating method, as opposed to a classical equating method, just the use of IRT kind of provides a holistic framework for your whole test operations, right? So like a lot of times test construction and form construction, item review will rely on IRT item estimates. And so we make use of these IRT estimates. Well, for building forms and for reviewing new items and their content or their statistical specifications, a lot of times uses IRT. And so having an IRT equating approach, an IRT scaling approach, just kind of makes for a holistic, everything is being done using the IRT metric or theta metric kind of. So that's kind of a nice benefit as well. It allows, in the instance of true score equating, it allows for immediate score reporting. But again, we have these costs, so it's, no one gets a free lunch here. We have stricter assumptions compared to the classical method. So now we have these IRT item level assumptions that really should be taken seriously and checked when possible, when the data allows that. And sometimes these assumptions are difficult to justify, but we've also seen in the literature that, mild to small violations of, say, the unidimensionality assumption, when that occurs, we don't see, a huge inflation of measurement error in these IRT equating results. And so in that sense, some of these IRT methods are robust to some violations in the sense that there's not a profound amount of measurement error being incorporated into the results. And so, but even so, we always want to strive for the gold standard of, as Cole and Brennan say, you always try to design your equating procedures in a way that it will lessen the impact of these assumption violations. So I always think of IRT as being fancy, but it's not better than classical equating methods, I wouldn't say, but it does allow you to do a little bit more in the operational world, I suppose. So yeah, that concludes this segment. We'll take a quick 5-minute break, and we will, when we come back, we will hear from Dr. Chris Hahn.
Jaime?
Yeah.
I noticed several questions in the chat box. Can you please check?
Oh, sure. I was going to go over questions at the very end.
Oh, okay.
To make sure that we had time for Chris to do his presentation.
And actually, my part will be very short, just like 10 to 15 minutes. So I don't know. We can maybe skip the break and we can just go straight and finish this session earlier.
Sure, that works. Yeah. Okay, then we'll go ahead and continue.
Okay. Hello, everyone. My name is Chris Han. Thanks, Jaime and Stella, for giving me this opportunity to share one of the software package I developed years ago, maybe about 15 years ago, while I was still working for my dissertation. So the software package I will be demonstrating and actually giving you some time to maybe to give you some hands-on workshop is about IRT EQ. As the name kind of indicates, it's about the IRT true score equating. And it actually not just covers the equating part, but also covers the rescoring of rescaling of the item parameters as well. I believe the email sent out to the participants already explained the software, the website where you can download this package. But let me just share my screen first. Sharing. Okay, I believe now everybody's seeing my desktop. So if you go to www.handtest.net, there is this very brief website where you can find some of the software packages available for you to download and install. Today, we will be using this IRT EQ. So if you click on this, there is some description about the IRT EQ. And basically, this is a manual of the IRT EQ, and you can actually find more comprehensive manual, user's manual document here. Software packages is here, you can download and install. And also, please make sure to download the example data as well. Assuming everybody had a chance to actually install the software, well, after you install, if you go to start button and type IRT EQ, then this software or app should be available in your start button. And let's click on this app. Then this is the main user interface of IRT EQ. And you should immediately notice some of the familiar names for the IRT scaling method and equating approaches here and there. And also, if you downloaded the example file, and that's zip file, so if you unzip that example file and go to the files here, this is the file you can find from the example file zip. And let's first go over the example first. So in this zip file, you can find two sets of IRT item parameters. So for one is for the test X and the other one is for the test Y. So test 1 or test X, you can just open it with a text editor, any text editor. Let's use Notepad that everybody has. So Notepad. This is nothing but a tab delimited text file. So first column basically indicates the item ID. So there are 21 items in this example, and there is a tab, and the second column is the IRT model. IRT EQ supports not only dichotomous IRT models, including 1, 2, and 3PL models, but also supports polytomous IRT models like generalized partial credit model, graded response model, all those models. And the third column indicates the number of response categories. Because we are using 3PL model, it's basically dichotomous model. So there are only 2 score categories, 0 or 1. So basically there are 2 score categories for all the items. And the following 3 columns are basically A, B, and C parameters, because we are using 3PL models. So A parameters, B parameters, C parameters. So that's the input file format for the test X or test 1. And let's take a look at the test 2 or test Y. Here in this example, we have a total of 66 items. And basically formatted the same. Item ID, the IRT model, number of response categories 2, and A, B, and C parameters, respectively. That's it. And in this example, this is actually real world examples I used to work on. So the real world scenario was like that, where the test X was the pilot test that was administered in the previous year. Say, let's say it was administered in 2020, year 2020. And after 1 year, the pilot program was successful, say, and this year we are expanding the same test program with more items. And between this test X and Y, we actually decided to use all of 21 items from the first year to be the common item for the second year. And the last 21 items in the second forms are the common items from the first year. So that's the scenario. Everyone's following so far? If you do, then would you mind to type just 1 in the chat box so that I can make sure everybody is following? Okay, great. So I see a large number of people following. By the way, please do feel free to work on your own IRT EQ. This is more, I wouldn't describe this as a demonstration of the software package, but more of a hands-on, workshop. So let's work together while you actually operate on your own IRT EQ app. So now we know 2 test programs. We already administered, collected data, and separately calibrated IRT item parameters for. So now we know the reference test, the base test from the last year, which was, so, and we need to open that file. So let's click on this open file. Oh, by the way, you need to click on this data tab and open file and find the location where you unzipped the example files. And let's open this testx.wingen.i file. This is the item parameter file. Once you open that file, you will notice there is 21 items now loaded up in this user interface pane. And now the second test from this year, let's open that up as well. So now we are going to open this test Y file and open. And from this year, we administered a total of 66 items. And I mentioned that the last 21 items from the second year are the common items from the first year. So the next step you want to do, well, first thing, you need to define which of those items are the linking items. So let's say item number 1 from test 1 and item 41 from test 2, they are the linking items. And once you click these linking items, you can click on this add button. And here you have 1 pair of the common items. And then the item number 2 from the first year, item number 42 from the second year, they are also linking items or common items. So add, you can continue to do that. By the way, after you add maybe just the 2 items, you can check the ABC plots. So here, or maybe these are the, well, I actually made a mistake. I will fix this issue, but it's not the issue of the software. I just defined the incorrect linking items, but I immediately could tell because once you click on ABC plot, it basically shows you the A, B, and C parameters under this scatter chart, scatter plot. And you can see the B parameters from year 1 and year 2, where actually we can add the label of the item numbers, item number 1 and item number 2, these 2 items were widely different from the reference line. So, well, it kind of tells you there is something maybe you want to double check. And yes, because as I just mentioned, we actually incorrectly defined the linking items. And there is actually the linking item list I already defined for us. So if you click on this open button, in the example file folder, you should be able to find the example 1 linking item list, LIL, and open that. Then now this is the correct list of the linking item. So here now we have 21 common items between these 2 test forms. And after you do that, now you can check the ABC plot again. Okay, now that this makes more sense. So now looking at these 21 common items, they are more of falling in the line on the reference line. Obviously, there are a couple of little bit of outliers, like item number 7 and 9, 17 and 9. That's B parameter. This is A parameter. Okay, A parameter is better. They are more similar with each other across 2 forms. C parameter, yeah, usually C parameters are unstable, a little more unstable when those parameters are being estimated. So you see some more outliers here and there. All right, so that's how you check the data. And you can also look at the TCC of these 2 test forms. So click on this plot TCC. And now there are 4 different curves. Let's look at one at a time. So first curve is the test 1 scoring items. So there were a total of 21 items, right? And this is the TCC of the test 1. And this is the TCC of test 2, the dashed line. Because there are a total of 66 items, it closely reaches to, asymptotically reaches to 66 as an expected score. And all of these 21 items actually were the linking items. So if you draw the TCC of the test 1 and test 2 linking items, they are almost similar with each other, although you see some difference in the lower end of the theta scale, right? But mostly they are very similar, which is good. This basically indicates that the test population from over the last year and this year were very similar. So that's not unusual. And there is this red line or curve that's in the region, but not in the chart itself, because we haven't run any rescaling yet. So we are going to just do that. So once our data is up and ready, okay, let's make sure everybody's following up to so far. So if you are following so far, would you type 2 in the chat box? Great, feedback. All right. So once your data is up and ready, we can go back to the method tab and choose which IRT item scaling method you want to use. You can use mean sigma, and maybe let's throw in stocking load as well here. And you can you need to now to specify whether the linking items are also used for scoring for the second test or not. It's very much up to your test design. Let's just simply say in this example, all the linking items are for the scoring as well. And if you don't use the TCC, you don't need to worry about this. But if you use the TCC, the stocking and load method or high bar method, you also need to specify the weight of the TCC when the loss function is computed. Loss function is basically the summary of the difference between 2 TCCs. And you can use uniform normal distribution or the actual distribution. The original method proposed by Stocking and Lord and Haibara both actually proposed to use actual individual test scores, individual test data. But if you know your shape of your score distribution, you can simply use normal or uniform. That's totally fine. Usually the use of normal distribution tries to minimize the difference in the magnitude of the loss function or difference in the two TCCs where the most of the candidates are, or the center of the theta score scale. But if you use a uniform distribution, it basically tries to minimize the difference in two TCCs across all the theta scale. In this example, let's just choose a uniform, and you want using the normal ogive metric, then you need to choose to use the descaling factor of 1.7. I think that's about it. So this is just so much for the rescaling of the IRT parameters part. And let's just stop there for now. And also we want to save the rescale the item parameters. And so click on this checkbox. The last thing you want to do is click on this browse button to specify your output file. So let's say our output file name is Equating workshop example 1, whatever you want to type in here, and just click on save button. And now all the files, output files, will be saved under this file name or something related to it. So I think that's it. We are ready to run the software. If you are ready, you can click on this blue button, initiate equating. Click on it. And depending on your computer speed, it should be done by now. It shouldn't take very much. So in our example, we actually asked our IRT to work on 3 different scaling methods, min, bin, sigma, TCC. So this is the output file. And this output file basically contains the mean discrimination, mean difficulty, and based on that, it actually computes the linear transformation coefficients A and B based on min, sigma, and TCC. Min, sigma, according to this output file, they are more or less very similar to each other. TCC method resulted in slightly different linear transformation coefficients. But again, if you look at the magnitude of the difference, it's just 0.01, 0.02-ish. So basically not much of difference, but there was difference for you to note. Okay, somehow my computer screen is frozen. Why? I don't know. Let me close that all and reopen. So basically, if you go back to the example file further, you should notice now 4 different output files. The first output file was the output file we just went over. And there are 3 output files. They are just new IRT parameters for the test 2 that's been rescaled to be on the same scale as the original or reference scale, which is from the year 1 test or test X. So this is there are 3 different files because we actually computed 3 different rescaling methods. The min, sigma, and Stocking and Lord. You can notice that there's these initials, min, mm, ms, min, sigma, SL, Stocking Lord. So there are 3 sets of files from 3 different methodologies. So that's so much for the scaling part. And you can use this rescaled IRT parameter values to develop your own true score equating policies or procedures. Or you can also ask IRT EQ to do that for you automatically. How do you do it? First of all, if you want to actually equate the scores, you actually need the theta scores from the test 2. So there is this file called examine underscore 700 WGE. This is again a simple text file, tab delimited text file with 2 columns. First column is examine ID. There are 700 test takers. And the second column is the theta estimate from the second test or test Y. So let's say, okay, so these theta values are based on the test Y's own scale. And now we just rescaled the test Y to be on the same scale as the test X, the last year's test, right? So we also need to equate the theta values from this year to be comparable with the last year's theta values. That's what we want to do, right? In order to do that, first you need to check these 2 different checkboxes. Save the equated scores, and produce the conversion table for you. And in order to do that, you need to supply the theta values here. So go to the data tab. There is this now newly available info box. Where you need to specify the file name for the theta values. So click on browse. And there is the examine underscore 700 file that we just went over. Let's open that file. Well, it doesn't do anything really. Just specify file name for that theta file, the theta data. That's it. And to just simplify, let's just stick to the stocking load. So I just canceled the min and min sigma, and just focusing on the stocking and load. And we are ready to click on this initiate equating button, blue button. Click on it. Okay, so now there is a new output file. So it gives you the basic, mean and standard deviation of the A and B parameters, and also the linear transformation coefficient A and B based on stocking and load. It also gives you the minimized loss function value as well, if you're interested. And it also describes in which file what data are stored. So let's close this alpha file and go to the folder. Now there are 2 new files, these 2 new files. So one file with this newly computed score extension NCS. If you click and open that with Notepad or any text editor, it basically gives you the number correct score that's equated to be comparable with the first year's test score, and how the IRT-EQ actually computed this. What's the basis of this test score equating? Then you can check this file, the conversion table, which is stored in the same file name with the extension of CON, conversion tail. Click on it. This is a typical conversion table. So how does it work? Basically, 3 columns. The first column is the number correct score from year 2, second year. And the third column is the expected score from the first year on the first year test score scale. And there is a theta value in the middle, which is the linkage between these two different number corrected scores from the two different years. So this is the conversion score conversion table, and you can notice that there is some rows with contents calling ID indefined, because we are using the 3-pair model. The lower asymptote is not exactly 0. It actually starts from, in this example, 14 out of 66 test items we had. So there is actually no straightforward way to equate these two test forms up to 14 items from the out of 66 items from the second year. So usually you need to come up with, the test developers need to come up with some sort of systematic way to address this issue. Most of common way is just identifying the common lower bound of the scores from both years. That's one methodology. Other methodology is you can develop some sort of interpolation of these two different test form scores. And a similar thing actually happens at the top end of the score scale, but not much, because it's, again, for the perfect score part, there is this theta value. For the perfect score, there is no definable theta value associated with the perfect score. So you need to come up with some policy with which you can define the upper bound of the theta value. But anything between the upper bound and lower bound, you can use this conversion table to find the score relationship between test form 1 and 2. So that's so much for the demonstration and hands-on workshop on IRT-AQ. Do we have any questions? You can simply speak up or type in the chat box. Okay, I will be watching the chat box, but if there is no question, I can hand it over back to Jaime.
Yeah, thanks, Chris. Yeah, I don't see any questions in the chat box. Thank you so much. That was a very thorough demonstration. Yeah, so there's actually, I was going through the questions, and I think the majority overall, or all of them actually, were about slides being shared, and then the Cullen and Brennan book that I was referencing. So the slides will be provided to everybody. We'll send those out after sometime today or tomorrow. I'll send those out so everybody who will have a copy, and I'll add a reference page to the slides to reference some of not just Chris's program for IRT-EQ, but also I'll reference some other free equating software, as well as the equating textbook that I was referencing by Cullen and Brennan. So I'll make sure I include all that in there as well. So if there's not any other questions, we can probably end early, unless anybody wants to ask a question that hasn't so far. Okay. Okay. Well, if you have questions later on, you can always reach out via email as well. Thank you so much for attending, and thank you so much, Chris, for your time and that great demonstration. I know you're busy. So next week we'll have Stella Kim. She'll be presenting her training session on multidimensional IRT equating. So hope to see you all there, and thank you so much. That's all. Take care.
Thank you. Bye.
Thank you.